Thank you, Aaron. Okay, so the probability um, that x is equal to x, we sometimes denote with this notation with the lowercase p for x an element of S. And well, these are the conditions for the probability mass function. The probabilities are greater than 0 for all x an element of S. And the sum over all values of x should be equal to 1. Okay. Okay. Okay, so those are just two terms not used by Amemiya, but you might encounter in other statistics books. The support of the distribution of x and the probability mass function. Okay. One popular distribution is the geometric distribution. When do you get a random variable that has a geometric distribution? So consider a sequence of independent Bernoulli trials, each having the same probability of success, P. Okay. Note that we encountered Bernoulli trials when we took the binomial random variable, which can be expressed as the sum of Bernoulli random variables. Okay. Let x denote the number of trials until the first success. The distribution of x is called geometric. We say x has a geometric distribution with parameter p, which is the probability of success in each trial. It's a probability, so it must be between 0 and 1. And usually we denote it by the random variable x has a geometric distribution with parameter p if the support of x is 1, 2, and so on. So it does not start with 0. And the probability mass function of x is as follows. Okay, so it's p 1 minus p to the x minus 1. Okay. Furthermore, the expected value of x is 1 over p. The variance of x is 1 minus p over p squared. Okay. So for example, excuse me. Okay, so let's say the Bernoulli trials is the birds. So a bird can either be the gender can either be male or female. Okay, and let's say the probability of each is 1/2. Okay, so let us have let us have y is equal to this is Bernoulli random variable. So y is equal to 1 or 0, 1 if male, 0 if female. So the probability here is 1/2. The probability here is 1/2. Okay, Q is 1 minus P. Okay, so let us have X is the number of trials till a male birth. Okay, so let me change the probability so it would be more, so it won't be, it would be less confusing. Don't erase. Mm. Mhm. So um, I'll just clear all. Um, my pencil is acting up. Okay, I'll just clear all from. Okay, so let us have the Bernoulli random variable 1 or 0, 1 if male, with probability P is equal to 3/4, 0 if female, therefore the probability is 1/4. Okay. So consider a sequence of random variables, each having the same probability of success. Let X denote the number of trials until the first success. So let X be the number of birds until you get a male bird. Okay. So what is the probability that X is equal to, say, 4? Okay, that you get male bird on the fourth bird. Okay, so that means that you have a sequence of 4 birds. So this is bird 1, bird 2, bird 3, bird 4. So you get a female here, female, female, then male. Okay, what's the probability of getting female? So they are independent trials. So for female bird is all 1/4, and for the male bird 3/4. Okay, so what is the probability? So it is 3, 4 to the 4th, or that is 3 over 256. So the probability is 0.011719, or approximately 0.012, okay, or 1.2%. So no, yeah. Okay, so is it consistent here? So you have P 3/4 times 1/4 to the third power, right? So you should get the same answer. So this is the probability that X is equal to 4. Okay. So actually, if you know how the geometric distribution arises, then even if you do not memorize this formula, you should be able to get the probability. Okay. Okay, so this is the mean and this is the variance. Okay. Note that the family of geometric distributions is described by one parameter P, the probability of success in a single trial. Okay. To have a geometric distribution, the trials must be independent and have the same probability of success in each trial. Okay. Okay. So note the difference between a random variable that has a geometric distribution and a random variable that has a binomial distribution. Okay. So you should be able to distinguish when you would have a geometric distribution in contrast to a binomial distribution. Okay. Another common distribution is the Poisson distribution. You would have this, for example, in econometrics, when we have the Poisson regression. Okay. Okay. So for the Poisson distribution, this can be described as a limiting case of the binomial distribution with parameters n and p, and the number of trials p as the probability of success per trial. Okay. So p comes from the Bernoulli distribution. Okay. Suppose that n Bernoulli trials must be performed in a fixed time interval. Okay. So this is how the Poisson distribution arises. You have n Bernoulli trials that must be performed in a fixed time interval. Okay. So for example, you would have the number of telephone calls in an hour, the number of cars passing through an intersection in an hour. Okay. So you have a fixed time interval. Suppose further that the number of trials is very large and the probability of success in each trial is very small. Okay. Okay, so we have so this is a limiting case of the binomial distribution. And we get that when the number of trials is very large and the probability of success in each trial is small. Okay. However, assume that the expected number of success is fixed. Okay. So here, for the binomial distribution, we have the expected value of x is n times p. The variance of x is n p q. Okay. So we assume that the expected number of successes is fixed. Okay, so this is just the binomial. So we assume that n times p is equal to lambda. Okay, that's why we have here the expected value of x is lambda. Okay, for some lambda greater than 0. Okay, so here lambda is between 0 and infinity. Thus, we have many trials with very small probability of success performed every 1/n of the time interval. The distribution arising in the limit as n approaches infinity, p approaches 0, while np is equal to lambda is called the Poisson distribution. Okay. So if you have a binomial random variable with parameters n and p, but you assume that the number of trials approaches infinity and p approaches 0 and np is equal to lambda, then the limiting distribution of the binomial distribution is the Poisson distribution. Okay. So we say that X has a Poisson distribution with parameter lambda between lambda has to be positive. Okay, and this is the notation. If the support of X and the probability mass function of X is this. Okay, so this is the probability mass function. Lambda to the X over X factorial e to the minus lambda. Okay. Note though, these expectations, the mean and variance are identical. Okay. At lambda. Okay. So some notes. The Poisson distribution is useful for modeling the number of arrivals, taxis, phone calls, web page hits in a given time interval, assuming that arrivals are independent. Okay. Say a use of the Poisson distribution in econometrics is the Poisson regression, where the left-hand side variable is count data. Okay. So for example, is morbidity or mortality. Morbidity. Okay. Where's that? We have our doctor. Our doctor is not here, Vijay. Morbidity refers to the number of people getting sick. Mortality refers to the number of people dying. Okay. So for those who would be taking health economics, you would encounter the terms morbidity and mortality. Okay. Calculations using the Poisson distribution are simpler than those with binomial probabilities. Okay. So note that we had so earlier we started with the binomial distribution, which is the sum of Bernoulli random variables. Then we had the geometric, trace again to the Bernoulli trials, and now we have the Poisson, which is linked to the binomial distribution. Okay, I want you to do this exercise This is quite involved. Okay. Suppose that the probability that a person is killed by lightning in a year is independently 1/500 million. Okay. So there's really is a small probability that a person would be killed by lightning in a year. Okay. Assume that the population of the country is 300 million. Okay. So so here you would get P. Oops. So you would get P here. So you would get P, and then you would get N. Okay. Okay. Compute the probability that 3 or more people will be killed by lightning next year. Okay. Exactly. Exactly three or more people will be killed by lightning next year. I want you to get the exact probability. Okay. Therefore, you have to use the binomial distribution. Okay. So let X be the number of people killed by lightning. Then X, the number of people killed by lightning, would have a binomial distribution where N is 300 million and P is equal to 1/500. Okay. So verify that the answer is this. Okay. We said that the Poisson distribution is a limiting distribution of the binomial if N approaches infinity and 300 million is quite large. P is 1/500 million, which is also quite small. Okay. So use the Poisson distribution. Okay. You can calculate N times P, which would be 3/5. So verify that this is the answer. Okay. So note that this is the exact probability and this is the approximate probability using the Poisson distribution. Note that the Poisson gives a relatively good approximation because the number of trials is quite large and P is quite small. Okay. Then approximate the probability that 2 or more people will be killed by lightning within the first 6 months of next year. Okay. Then approximate the probability that in exactly 3 of the next 10 years, exactly 3 people are killed by lightning. Okay, so do this exercise for the Poisson distribution. Okay. Okay. So those are some discrete distributions. The geometric, the Poisson, distribution. Okay. Now let's go through some continuous distributions. Okay. Okay, so we've encountered several continuous distributions before. In this section, we had the F distribution, the T distribution, and the chi-square distribution, which are continuous distributions, which are related to the normal distribution. Okay. Okay. So common continuous distribution, which we have used in the course, is the uniform distribution. Okay. So the uniform distribution, the notation is this: X is distributed U over the interval with endpoints A and B. Okay. So the density function of a random variable that takes a uniform distribution is this. Okay. And you can verify the these are the mean and the variance. Okay. So for the mean, then you just have to use the integral of x, f of x dx from minus infinity to positive infinity. For the variance of x, then you use the integral of x minus mu squared f of x dx from minus infinity to positive infinity. Then you should get this. Okay, so our common example was what we use often before was the uniform interval over 0, 1. X having a uniform distribution over the interval 0, 1. And this would be 1. So you would have f of x is equal to 0 if x is less than 0. It would be equal to 1 if x is between 0 and 1, and 0 if x is greater than 0. Okay. But then you can have, let's say, a is equal to minus 2, b is equal to 2. Okay, so 1, 2, minus 1, minus 2. So what would be the density function? So this would be 0 if x is less than minus 2, 0 if x is greater than 2, or you can have less than or equal, and you would have 1, b minus a is 1/4. So that is if x is between minus 2 and 2. Okay, so note that this is f of x. So beyond 2, f of x is 0, less than 2, f of x is less than 0. So that is the uniform distribution. Another example is the exponential distribution. Okay, so this is a continuous distribution. The exponential distribution is a distribution for the waiting time for some random event. For example, for a light bulb to burn out, or for the next earthquake of at least some magnitude to occur. Okay. So in a way similar to the geometric distribution, but this is the continuous distribution counterpart. Okay. Okay. The exponential distribution is a distribution for the waiting time for some random event. In some models, a researcher would like to know the probability of a variable which measures how long it takes for an event to occur. For example, how long does a strike last? How long does unemployment last? Okay. So the density function is of this form. Okay. Okay, so for x greater than equal to 0, is lambda e to the minus lambda x. And these are the variances, expected value and variance. Okay. You can also verify this using the formulas for the expected value and the variance. Okay, so what are other properties of this exponential distribution? Okay, so you have the probability that x is greater than equal to x is equal to e minus lambda x. Okay. Okay, so you can verify that also. Okay. So how do you get that? Then that is the integral of f of x dx from x to infinity, right? See if you can get that. And then you can get also the probability that x is less than x, which is the CDF, right? And that would be 1 minus e to the minus lambda x. Now, what is one special feature of the exponential distribution? It has a memoryless property. Okay. The probability that x is greater than equal to x plus y, given x is greater than equal to y, is equal to e to the minus lambda x. Okay. Okay, so you can already also verify this, that you get that expression. Okay, note that this is a conditional probability. Okay, the memoryless property means that if the event has not occurred by some given time, no matter how long, the distribution of the remaining waiting time is the same as it was at the beginning. There's no aging. Okay. So that's applicable, for example, when you're looking at the probability of the next earthquake. Okay. Like there's a question, if an earthquake has not occurred for the last 100 years, how likely is it that is the probability of an earthquake increasing? Is it more likely then to have an earthquake occurring in the near future? Okay. Okay, do this sample problem. Assume that a light bulb lasts on average 100 hours. Okay. Assuming the exponential distribution, compute that the probability that it lasts more than 200 hours and the probability that it lasts less than 50 hours. So you calculate the probability that let x be the waiting time for the light bulb to burn out. then X would have an exponential function, exponential distribution with this as the parameter lambda. Okay. How do you get that lambda? Lambda here. So you get here, lambda is 1 over the expected value of X. But you're given that the light bulb lasts on average 100 hours. Okay. So you would have 1 over 100 for lambda. Okay. So the probability that X is greater than 200, then you just use this formula. The probability that X is less than 50, then you just use the complement and you get this. Okay. So note that a light bulb is 3 times more likely to last less than 50 hours than to last more than 200 hours if the average hours is 100 hours. Okay, so this just some examples of the continuous distribution. Okay. So we have the uniform distribution and the exponential distribution. Okay. So you would see this functional form quite often in exams and exercises. Okay, any questions? So the coverage of the test would be, the coverage of the midterm would be up to this point. Okay, okay, so let's start with large sample theory. That won't be covered in the test, okay, but in the second test. Okay, I have uploaded this file earlier in the UVLE. Okay. Okay. So we would be starting with large sample theory, which is quite important because once you get out in econometrics, once you get outside the Cost-Markov framework, if you have these violations, you get alternative estimation methods. And usually for the test of hypothesis, the properties of the estimators, the test of hypothesis, you have to appeal to large sample theory. Okay, so the nice properties of estimators and the test of hypothesis are usually interpreted in the context of large sample theory. Okay. Okay, so for large sample theory, to anticipate what you would have later on. Okay, so far in part one of the course, the first half of the course, we dealt with characteristics of the population. Okay. So we had practically full information on the population. Okay, that's why. Okay. So in part two, we would be going into sampling. We don't have full information on the population, and our information comes from samples. Okay, which would be observations assumed to be coming from the same underlying population. Okay. So suppose you want to study the population of the Philippines. You do not have data on everyone in the Philippines, but your data is limited to some sample observations or just a subset of the population. Okay, so let us denote the sample size by n. Okay, so note that for those who have taken econometrics in their undergrads, you have the Gauss-Markov theorem, where you get the nice ordinary least squares properties. And these nice OLS properties are small sample properties. So they hold for fixed n. Okay. Okay, but once you have violations of the Gauss-Markov theorem, then you have appeal to the large sample properties. So you would be looking at what happens when n approaches infinity, when you have sufficiently large sample size. Okay. Okay, so we will be looking at large sample theory concepts related to what happens when n approaches infinity. Okay, which, okay, in the sampling context, it is when you have a sufficiently large sample size. Okay. Okay, so in this section, we would be looking at convergence concepts and limit theorems. Okay. Okay, so for convergence concepts, we would look at the simplest convergence concepts. If you look at other statistics books, also other econometric books, there are different convergence concepts. Okay, we will just be taking the most basic ones: convergence in probability, convergence in mean square, and convergence in distribution. Okay, so the notation here is the random variable x sub n converges to x in probability. The random variable x sub n converges to x in mean square, and the random variable x sub n converges to x in distribution. Okay. After taking the convergence concepts, we would look at the limit theorems, the weak law of large numbers, and the central limit theorem. Just like the convergence concepts, there are different versions of the law of large numbers and the central limit theorems in other books, but we would be just looking at the most basic concepts. Okay, so for the weak law of large numbers, okay, so we would have, for example, let R be the number of heads in n tosses of a coin. Okay. But we do not know the probability of heads in a toss of a coin in the population. Okay, in the underlying data generating process. So this is the probability of heads in the toss of coin in the population. Okay. But suppose we run an experiment, we have n tosses and count the number of heads in n tosses of a coin. Okay. So this is from the sample. Okay. And it turns out that R over N converges in probability to the population probability of heads in a toss of coin. Okay, so here we use the concept of convergence in probability. Okay. In general, the weak law of large numbers says that the sample mean approaches in probability the population mean. Okay. Okay. So the population mean is unknown. If we do not have full data on the population, the sample mean is based on what you observe in your sample. Okay. Okay. For the central limit theorem, I think we will be taking two versions. One of the central limit theorem says that the binomial random variable approaches the normal random variable in distribution. So you need this concept. Okay. So what is interesting here is that you have a discrete random variable approaching the distribution of a continuous distribution. Okay. So based on this, you can have a normal approximation to the binomial distribution. Okay, that's an application of this finding. Okay. So let us go over these convergence concepts. Okay. Okay, so let's first take the concept of convergence of a sequence of real numbers. Okay. So this is what you would have had in your math classes, a convergence, the convergence of a sequence of real numbers. Okay. A sequence of real numbers is said to converge to a real number alpha. Okay. Alpha n converges to alpha as n approaches infinity, or the limit of alpha n as n approaches infinity is equal to alpha. So these are just equivalent notation for denoting the convergence of a sequence of real numbers. Okay. And the definition is when do we say alpha n converges to alpha as n approaches infinity? Okay. For any epsilon greater than 0, there exists an integer n such that for all n greater than big N, we have the distance between alpha n and alpha is less than epsilon. Okay, so this says that, okay, so suppose this is the real number line. We have a sequence of real numbers. When do you say alpha n converges to alpha? Okay, okay, so for any epsilon, okay, so this is epsilon. This is also epsilon. Okay. So beyond alpha n, let's say alpha n plus 1, they all would lie alpha n plus 2 and so on. They would all lie within this interval. So the distance between alpha n minus alpha, once n is greater than big N, the succeeding numbers would all lie within this interval. Okay. Okay. Okay, the absolute value of alpha n minus alpha is just the distance between alpha n and alpha. Okay. So you would have taken that in your earlier calculus class. Okay. So let's have an example. Let C sub n be 5 plus 2 over n. What is the limit of C sub n? Okay, so you get the limit of 5 plus 2 over n as n approaches infinity. Okay, so what is the limit? The limit of 5 is 5. The limit of 2 over n as n approaches infinity, n becomes a very large number. So the limit is 0. So the limit of C sub n is equal to 5. Okay. How about the sequence minus 1 to the n? N is equal to 1, 2, and so on. Okay. So here, so you have n 1, 2, 3, 4, 5, and so on. So minus 1 to the n. So this is minus 1, 1, minus 1, 1, minus 1, and so on. Okay. So the sequence just flips from minus 1, 1, minus 1, 1, so on to minus 1, 1, so on. Okay. And note that this sequence has no limit. Okay. So basically, you can see from the convergence of a sequence of real numbers what you mean by the limit. Okay. Now, we look, instead of looking at a sequence of real numbers, we look at a sequence of random variables. Okay. So let's look at convergence in probability. Okay, a sequence of random variables x sub n is equal to 1, 2 is said to converge to a random variable x in probability. So you have here x sub n converges to x in probability as n approaches infinity, or you have it here, the p-lim of x sub n as n approaches infinity is equal to x. Okay. Okay. Later on in econometrics, you would be working with this p-lim, okay, the probability limit. Okay, so this sequence of random variables, so this means x sub 1, x sub 2, x sub 3, so on to x sub 1000, x sub 1001, and so on, okay, to infinity. Okay, so what do we mean by convergence in probability? Okay, for any epsilon greater than 0 and delta greater than 0, there exists an integer n such that for all n greater than n, we have the probability of the distance between x sub n minus x is less than or equal to epsilon is greater than 1 minus delta. Or equivalently, the limit of this probability is equal to 1 for any epsilon greater than 0. Or if you take the complement, then the probability is equal to 0 for any epsilon greater than 0. Okay. Okay. So note the modification of the definition of convergence of a sequence of real numbers to account for the probabilistic nature of random variables. Okay. So whereas before you just have epsilon greater than 0, now you have delta greater than 0 appearing here. Okay. So you have okay. Note that for the convergence of a sequence of real numbers, we don't have probability. So we simply have this. Okay. So you have simply alpha n minus alpha, the distance is less than epsilon. This is for the sequence of real numbers. Okay, but since now we have random variables, then we have this probability. Okay. And this. Okay. The second and third lines here are just rewriting of this equation. Okay, so let's have an example. Okay, so let C sub n be a sequence of univariate random variables such that the probability of C sub n is equal to C is 1 minus n minus n to the minus 1 or 1 minus 1 over n. Okay, so this can be expressed as this. Okay, and the probability that C sub n is equal to n is n minus 1, n to the minus 1 or 1 over n. Okay. So note that there are only two possible outcomes, right? Either C sub n is equal to C or C sub n is equal to n. Okay. It can be shown that as n approaches infinity, C sub n approaches C in probability. Okay. So this notation is just this expression also. The p-lim of C sub n as n approaches infinity is equal to C. Okay. Let us see how this works. Okay. So let us have n, C sub n be a sequence of real of univariate random variables. So let us have 1, 2, 3, 4, so on to 10, 20, 100, and so on. Let's say even 1,000. Okay. So what would be two possible outcomes? Either C sub n is equal to C, where C is a constant, or C sub n is equal to n. Okay. Okay, so let us look at the probabilities. C sub n is equal to n. Okay, so let us get first the probability that C sub n is equal to n. That is 1 over n. So that is 1, 1/2, 1/3, 1/4, so on to 1 over 10, so on to 1 over 20, so on to 1 over 100, so on to 1 over 1,000, and so on. So note that as n becomes larger, okay, so you have C sub 1, C sub 2, C sub 100, C sub 1000, and so on. Okay. But the random variable can either be C, it can either be C or N. Okay. So C sub 1 can be C or N, which is 1. Okay, so this is 2, this is 100, this is 1000, so on. Or it can be C, okay? So C sub 1 can be C or 1, C sub 2 can be C or 2, C sub 100 can be C or 100, C sub 1000 can be C or 1000. Okay. Okay, so what is the probability that Z would be equal to N? Okay, so it depends on N. So note that the probability decreases the larger N is. Okay. While over here, this would be 1/2, 2/3, 3/4, 9/10. This would be 19/20. This would be 99/100, so on to 999/1000. Okay, so note that you have this. Okay. Okay, so what is the probability that C sub N is equal to C as N approaches infinity? So what is the limit of this probability? Okay, so what is the limit of the probability that C sub N is equal to C as N approaches infinity? So you can see that the probability approaches 1. Okay, how about this? What is the limit of the probability that C sub N is equal to N as N approaches infinity? So you can see that the limit would be 0. Okay. So we get this result. Therefore, as N approaches infinity, C sub N would approach C in probability. That is, the PLM of C sub N is equal to C. Okay, so do you get that? Do you have questions there? Do you see that? So that is what we mean. That's an illustration of what we mean by convergence in probability. Okay, so the random variable C sub N approaches C as N approaches infinity. Okay. Okay. Here are some rules on getting prelims. You should be doing this automatically later on as you do more econometrics. Suppose the prelim of the random variable x sub n is C, the prelim of the random variable y sub n is equal to D. So it turns out that the operations, the prelim operation is very simple. What is the prelim of xn plus y sub n? That is just C plus D. The prelim of x sub n, y sub n is CB. The prelim of x sub n over y sub n is equal to C over D. Okay, so it's simple. For the rules, what is the prelim of x sub n plus y sub n? The sum, then that is just the prelim of x sub n plus the prelim of y sub n. For the product, what is the prelim? Then that is just the prelim of x sub n times excuse me. Then there's the prelim of x sub n times the prelim y sub n. Okay. What is the pilum of x sub n over y sub n? Then that is just the pilum of x sub n over the pilum of y sub n. Okay. Okay. So you would need the concept of convergence in probability when we go to estimators in econometrics. You need the concept of convergence in probability, these P-lim operators, to show consistency of estimators. So I'll stop at this point. So try to observe first with regard to large sample theory and the convergence concepts. So take it a step at a time. So for today, understand first the convergence of a sequence of real numbers. That would just be a review of your earlier calculus class. And then try to absorb the concept of convergence of a sequence of real numbers, particularly convergence in probability. Okay, so just the first step here. So you won't be overwhelmed. Okay. So contrast convergence of sequence of real numbers and convergence in probability of a sequence of random variables. So try to rework this example. Okay. Any questions? So I'll try to upload this weekend the problem sets. Okay, and our first test would be November 10th. Yeah.
Ma'am, question po for the midterms.
Yeah, sure.
Are we allowed to use calculators po?
Yeah, you are allowed to use calculators, but please no cell phone. You cannot use the calculator function in the cell phone so that you can communicate.
Okay po, ma'am. Thank you po.
Sets. Okay. We will be providing blue books and swatch papers. Okay. Yeah. So just try to review your notes, the sample, the examples. Try to refer also to Amemia's book and find another book which you're comfortable with, because Amemiya can be quite terse. It's like variance book, not too many words. So you can look at for the simpler books, Hagen Craig, Larson. For the other books, somehow I maybe for the latter part of, well, I also like Moodgrave, William Bays, and also Poirier is also good. Mittelhammer is also a good book, but then there's just too much. There are just too much in Mittelhammer. You do not need all that stuff for this course. Okay, it's a relatively simple book with many examples, but there are just so many details that sometimes can be overwhelming. Okay. Okay, so that's it. So other questions? Okay. So enjoy the reading break. Try to recharge. I will do that also. Okay.
Thank you po, ma'am.
Thank you po,
So
ma'am.
take care. May new variant, kaya mag-ingat kayo lahat. Okay. So November 10 would be our midterms. Okay. So don't panic. Study first. Okay.
Yes po, ma'am. Thank you po.
Okay.
Thank you po.
As we go along, then it will become easier. Okay. Sige. Okay. Have a nice break.
Thank you, ma'am.
See
Thank you po, ma'am.
after November 1. Okay.